Between algebra and calculus, we have all of the tools we need to do a really good job at graphing some of the basic functions. So let's start with a bit of a graphing strategy, and then we'll work through the graphing strategy in an example. The first thing we're going to want to do is identify the domain of the function and the x and y intercepts. Any holes the function might have. Remember, holes are where we have removable discontinuities. And then any vertical or horizontal asymptotes. So that's the first step of our graphing strategy. And let's look at a specific function and start with that. So let's look at the function f of x equals 9x over x cubed plus 1. And we'll start with number 1, and we'll work through a whole graphing strategy, and then we'll see the graph of this function come together. So step 1 is finding the domain of this function. And remember, the domain is all of the x values that you can plug in, which means we should look for the x values that we cannot plug in. And when we have a continuous function, that function has no, for example, zeros in the denominator or negatives in the square root. This function specifically has a denominator. There are no roots, but there's a denominator. So we'll see when x cubed plus 1 is equal to 0, which is when x cubed is equal to negative 1, which is only true when x is equal to negative 1. And so we have a problem when x is equal to negative 1, and so our domain is actually going to be negative infinity to 1, not including 1, unioned with, negative infinity to negative 1, because we have a problem when x is equal to negative 1, unioned with negative 1 to infinity. So our domain is just not including negative 1. We have something happening at negative 1. The second piece here is finding the x and y intercepts. So let's start with that. F of 0, when x is 0, we have our y-intercept is equal to 0 over 0 plus 1, which is equal to 0 over 1, which is equal to 0. And so our y-intercept is equal to 0, which means the point 0, 0 is a point on our graph. And I will, maybe in a different color, circle the important things here. We have our domain, we have our y-intercept. Our x-intercept is when we have 0 equals 9x over x cubed plus 1. When y is 0, we have our x-intercept. And we can multiply both sides by x cubed plus 1, and we get 9x equals 0. Divide by 9, x equals 0. Our x-intercept is equal to 0. And I mean, that makes sense, right? Because we found the point 0, 0 on the graph, and if we were to draw a graph, we would see the point 0, 0 crosses both the x and the y-axis. So we have our domain, we have our x and y intercepts. We can look for any holes or vertical or horizontal asymptotes. So holes would be removable discontinuities. I don't see any removable discontinuities, but I do see a discontinuity, right? I see that something weird happens when x is equal to negative 1. And if there's not a hole there, if the discontinuity is not a hole, we know it's not a jump because we don't have a piecewise function. So we have an infinite discontinuity, which means we have a vertical asymptote at negative 1. Remember, if there was a hole, this would be a removable discontinuity, which means with a little bit of algebra, we'd be able to remove the discontinuity. We would be able to adjust the function such that that discontinuity was removed. So we have a vertical asymptote at negative 1. We can also look for our horizontal asymptotes. Horizontal asymptotes occur when the limit as x goes to infinity of our function is equal to a value. And we can use an auxiliary function. We can say this is the limit as x goes to infinity. Let's just look at the highest exponent in the top and the bottom. 9x over x cubed. We can cancel an x. This is equal to 9 over x squared. And as x goes to infinity, as x gets really big, we get 9 over 10, 9 over 100, 9 over a million, 9 over a trillion. As x goes up, we're going to get a really, really small number, something really close to 0. And so we have a horizontal asymptote at 0. Awesome. So continuing, we have our asymptotes, we have our domain, we have our intercepts, we have our holes. Let's go on to point number 2, which is we can find the intervals where f is increasing or decreasing and local extrema using, hopefully we all know what we're going to use to find where we're increasing, decreasing, and local extrema, using the first derivative. And we'll call it the first derivative test. So what we have is our function, which is f of x equals 9x over x cubed plus 1. And we need the first derivative of this. We'll use the quotient rule, which is low d high minus high d low all over low low. F prime of x then is going to be low d high, 9 times x cubed plus 1, minus high d low, 9x times the derivative of the bottom function here is going to be 3x squared all over low low, which is x cubed plus 1 squared. Multiplying out, we get f prime of x is equal to 9x cubed plus 9 minus 9 times 3 is 27x cubed over x cubed plus 1 squared, which is equal to 9 minus 27 is 18. Negative 18x cubed plus 9 over x cubed plus 1 squared. We can also continue, we can factor the top, and we can say this is finally equal to, f prime of x is finally equal to, pull out a negative 9 times 2x cubed plus 1 over x cubed plus 1 squared. And when I pulled out a negative 1, I should have said that this was minus 1, because this sign switches and this sign switches. Now with our first derivative, we're going to look for critical points. The critical points of this function are the places where f prime of x is equal to 0 and the places where f prime of x does not exist. So when f prime of x is equal to 0, we have a simple case where we can multiply the denominator by both sides, and we're left with negative 9 times 2x cubed minus 1 equals 0. We can divide by the negative 9, we're left with 2x cubed minus 1 equals 0. X cubed equals 1/2, which means x is equal to 1 over the cube root of 2. And so that's where we have our local extrema of some sort, maybe. And then if we look at where f prime of x does not exist, that's where this denominator is going to be equal to 0. which is when x cubed plus 1 squared is equal to 0, which once again is at x equals -1. Which makes sense. If the function doesn't exist at x equals -1, then the derivative is definitely not going to exist at that point. And so we have our two important points, our 2 points where the function could be switching. If I put them on a number line, I have -1, and then I have 1 over the cube root of 2. And I want to know where this function is increasing and decreasing on this number line. And so let's go back to our derivative. Let's go back to our derivative up here, our f prime, and plug a few numbers in. And those numbers have to be something to the left of -1. So we'll plug in, say, -2. We'll plug in something between our two important points, so maybe 0. And then something to the right of our 1 over the cube root of 2, maybe something like 1. And so if I plug in -2 to our function, let's grab our function real quick. I think I can do that like this. I can copy it, bring it down. Here we have our derivative again. If I plug in -2, I get f prime of -2 is equal to -9 times 2 times -2 cubed minus 1 over -2 plus 1 squared. And now let's think about this for a second, because we don't actually have to do all of this math. This term's going to be negative. We're going to take 1 away, and then we're going to multiply by a negative number. So the numerator is going to be positive. The denominator is something squared. Well, something squared is always positive as well. So positive over positive equals positive. And so to the left of -1, we are increasing. Our function is increasing. Now I can plug in 0. F prime of 0 is equal to -9 times -1, because our x term is just going to go away, over 1 squared. On the top, we have a negative multiplied by a negative, which is a positive. And on the bottom, we have something squared, which again is a positive. And so between -1 and 1 over the cube root of 2, we also have a function that is increasing. Now we need our third point. We said f prime of 1. And if I plug 1 into my derivative, I get -9 times 2 minus 1 over something negative, or something positive, because it's 1 plus what's 2 squared. So in the numerator, I have -9 times 1, which is a negative, over 2 squared, which is a positive. So we actually get something decreasing on the right. And so we have, I can do one of my circles here. We have where this function is increasing and decreasing. And our local extrema. Specifically, we see that we are increasing to the left of 1 over cube root of 2, and we're decreasing to the right of it. So if we're going from increasing to decreasing, we can see that we're going to have a local maximum. We can see very clearly there that there will be a maximum there. Okay, let's move on to item number 3, which is finding intervals of concavity. Intervals of concavity and inflection points. We're going to find intervals of concavity and inflection. And to look at concavity, we're going to need to look at the second derivative. So let's go to the first derivative. F prime of x is equal to -18x cubed plus 9 over x cubed plus 1 squared. And we're going to need the second derivative this time. So let's find the second derivative, f double prime of x. We're going to need to do our quotient rule again, low d high minus high d low over low low. And so we have the low function, x cubed plus 1 squared, d high, multiplied by 18 times 3 is 30, 40, 54, negative 54x squared, minus high d low, our, let's move this down. I'll move it up, I'll put it right up here. Minus high d low, we're going to have negative 18x cubed plus 9. The derivative of the lower function, this is going to be the chain rule. We take the derivative of the inner function, which is just going to be 3x squared, multiplied by the derivative of the outer function, which is going to be 2 times x cubed plus 1, 2 times the inside. And all of that is over low low, which is x cubed plus 1 squared squared. And when you have a power to a power, you multiply them together, and so this is just going to be x cubed plus 1 to the 4th power down in the denominator. Now let's do a little bit of algebraic manipulation. Let's simplify this a little bit. I see that x cubed plus 1 squared is right here, x cubed plus 1 to the 4th is right here, and x cubed plus 1 is right here. I can cancel one of them, right? I can cancel that one, all of that, and I can make this a 3. And so we are already a little bit simpler, which is f double prime of x is equal to x cubed plus 1 times negative 54x squared minus negative 18x cubed plus 9 times 3x squared times 2 all over x cubed plus 1 cubed. Now I can multiply everything out in the numerator. It's not too challenging to multiply everything out up there. Negative 54x squared times x cubed is going to be negative 54x to the 5th. Multiply it by 1, we get minus 54x squared minus, well, minus is going to be a plus. 18 times 3 times 2. 18 times 2 is 36. 36 times 3 is 108. So we're going to get plus 108 x to the 5th. Then we have minus sign distributing with a plus sign, so we're going to get a minus 9 times 3 times 2 x squared, or 54x squared. Still all over x cubed plus 1. Now I can combine like terms. We have negative 54 plus 108, and then we have negative 54 minus 54. So I get f double prime of x is equal to 54x to the 5th minus 108x squared all over x cubed plus 1 cubed. Now to find the important points for f double prime, we find the values where f double prime of x is equal to 0, or where f double prime of x does not exist. And the points where f double prime of x is equal to 0 are exactly the points where 54x to the 5th minus 108x squared is equal to 0. And those 2 points are, well, when x is equal to 0, that's a simple one. When x is equal to 0, this function is equal to 0. And then if we pull out x squared, and we can pull out 54, we see that it's also when x cubed minus 2 is equal to 0. Which is when x is equal to the cube root of 2. And then we also need when f double prime does not exist, and when f double prime does not exist is once again that same point, which is when x cubed plus 1 equals 0, or when x is equal to negative 1. And so now we're going to do another sine chart. We're going to look at the points between -1, 0, the cube root of 2, and that's all of our points. So we're going to look all around that for f double prime. So once again, I'm going to make a copy of f double prime of x, and we're going to use it. So we need a point to the left of -1. So we can say -2. We need a point between -1 and 0. So let's say -0.5. Let's go right in the middle. Then we need a point between 0 and the cube root of 2. Well, the cube root of 2 is definitely bigger than 1, so we can use 1 again. And then we need a point bigger than the cube root of 2. We can use 2. Okay, so let's look at this. F double prime of -2 is going to be 54 times -2 to the 5th, which is going to be a pretty big number, minus 108 times -2 squared over -2 plus 1, -2 cubed plus 1 cubed. And once again, I'm not going to work this out. I'm just going to look at the top and see that I have a really big negative thing, and I'm subtracting something from it because we have -2 squared here, so that's going to be a positive number, and we have a minus sign. So we're going to get something super negative on the top, and then -2 cubed plus 1 is obviously going to be negative. Cube that, it's still going to be negative. We end up with a negative over a negative. So f double prime at -2 is going to be positive. So to the left of -1, the second derivative is positive. Now we're going to do the same thing with f double prime of -0.5. And when I plug in -0.5, the numerator is going to work the same way. I'm going to get a negative number minus a positive number, which is going to be something super negative. So we get negative on the top. And then the denominator, 0.5 cubed, is something smaller than 0.5. So the denominator this time is actually going to be positive. -0.5 times -0.5 is -0.25. Multiply it by -0.5 again, and you get, it's going to be 0.25. And then multiply it again, you're going to get negative something really small. Plus 1 gives you a positive number. And so we're actually getting a minus sign in between -1 and 0. Plugging in the point 1 is pretty easy. The denominator is definitely going to be positive. F double prime of 1. The denominator is definitely going to be positive because we just have 1 plus 1 cubed. And then in the numerator, we're plugging 1 in. 54 minus 108 is negative. So we get negative over positive. I'm going to get another minus sign here. Lastly, we want to look at f double prime of 2, positive 2. The denominator, again, we're plugging a positive number into a positive function. We're going to have a positive denominator. And then the numerator, 54 times 2 to the 5th minus 108 times 2 squared. This one's a little bit tougher, but 2 to the 5th is much bigger than 2 squared. We're going to end up with a positive minus a smaller negative, which is going to be positive over positive. And so we're going to get a plus sign over here. Now this has been a very long problem, but let's finally put all of our pieces together and try to graph f of x equals 9x over x cubed plus 1. And we'll start at the top. The first thing we found was that the y-intercept and x-intercept are both at 0, which means we have a point that's crossing at 0, or we have the point 0, 0. The next piece of information, we also found the domain, which was we had a vertical asymptote at -1. Vertical asymptote at -1, so let's plot that. Let's go to the point -1 and just put a vertical asymptote here. part 2, we found the derivative, we found all of these critical points. We found a critical point at -1, which we know about, and also 1 over the third root of 2. That's going to be, let's just put that right about here. This is 1 over the third root of 2. X equals 1 over the third root of 2. And so that's our critical points. Those are the 2 points where we have something weird going on, or we have a local min, max, or a saddle point. And in fact, from this graph, we found that it was a max, that we were going to be going up at that point and then curving down. And so if I go down to the graph here, I'm going to have something like this right at that point. And we can go even further. We know that our graph is going to touch 0 right here. So we have a first little piece of our graph. And since we don't have another inflection point, we don't have another point that's changing things, this is going to keep going down. And so we see that it's going to be negative infinity as we approach -1 from the right. Perfect. Let's keep going. We also found, I forgot to circle it in blue, but we also found that we had a horizontal asymptote at 0, which means as we keep going on the right here, we're going to be approaching 0. We have a horizontal asymptote at 0. And so we're going to be going off to 0. Awesome. We also found that we're increasing to the left of -1. Increasing to the left of -1 means we have to have a function that's increasing like this. We have no other inflection points, so we also know that we're not going to see any other local mins or maxes. Nothing weird's going to happen to the left of the function here. We actually don't really need our second derivative test, but our second derivative test does tell us to the left of -1, we're increasing the whole time. Our derivative's increasing the whole time. And so we have something that looks like this. We have our horizontal asymptote at 0. And so the second derivative was a tough part, and the second derivative is actually not something we really needed, and we end up with a graph that looks a little bit like this. Now your task, a little homework problem for you is go to Desmos graphing calculator and plug this function in and see how close we got, and see how powerful the derivatives and understanding functions can be in understanding the shape of the function and the graph of the function.